Hey, Physics 100, this is Dr. Ricardo. We're doing the second half of Chapter 5, which is on fossil fuels. There'll probably just be 2 videos for this chapter. So we are up to talking about what it means to refine the petroleum that you extract from the earth. So refining is the separation of compounds by distillation. So first we're going to talk about what that means and what the different fractions are. And then I'll show you a couple of pictures from the old book that are related to distillation. So the concept of distillation is, since the crude oil is made up of many different chemical compounds, these chemical compounds have different boiling points. So when you heat up the crude oil, they will boil at different points. So depending on where you look in the fractionating column and what the particular temperature is, that's the different chemical compounds that you'll extract. So when you see an oil refinery, and there's some of them in New Jersey, when you're down by Newark Airport, the city is called Carteret, New Jersey. So in Carteret, New Jersey, you look out to the right and you see Newark Airport. You look out to the left and you just pass IKEA. And you also are right around the entrance to the Goethals Bridge that goes over to Staten Island. So in that portion of New Jersey, there's a lot of oil refineries. Okay, so the way the oil refinery works is that you take crude oil and you put them into a distillation chamber. And the distillation chamber, let me see if I can get a picture from the new book. That would probably help. And then we'll go through these fractions. So this is from Chapter 5 of the new book, right, which is on fossil fuels. I think they have a good one. All right, so this is probably the best one to look at. All right, so let me just autofocus a little bit. Is that okay? Maybe a little better. Let's go back a little bit. All right, that seems to be about as good as I'm going to get it. Okay, so this is figure 5.4. So you should have this in your notes to refer to in the new book, which is by Wolfram, by Richard Wolfram. Right, so in that book, I put these on the Moodle. Okay, so you should be able to find this picture. Okay, so the idea is the crude oil goes through this set of pipes. So you put the crude oil in here. Remember, it's very thick and black. It's got a lot of different, like hundreds of different chemical compounds in there that are useful, and some junk in there too that we want to get rid of. Okay, so when it goes through this furnace and it's pumped through this furnace, it gets heated up. Okay, so this concept we've seen over and over and over again. It's the idea of a heat exchanger. So the furnace is heating up the crude oil without burning it. Right? There's no oxygen inside this tank. We're not burning the crude oil at all. It's just going to get heated up. So by the time it makes it out over here, it's about 400 degrees Celsius. Okay. So what happens is it starts to boil. And as those compounds boil off, they make their way through. So down here is all liquid. Okay. So they make their way through these pipes here. And if you look pretty smartly, these pipes have little caps on them. Okay. And so what happens with those little caps is that the gases can escape and make their way up to the next section and make their way up to the next section, as long as they still are at a temperature in which they would still be a gas. So they have to be the smaller and smaller molecules. Anytime you have any precipitation, right, any condensation, the condensation is going to form on the walls here and drip back down. But it can't drip back into this pipe to make it to the next lower chamber. How come? Because it has this little cap over it. So I'm going to draw that bigger in a second. So notice you see that in each of the different chambers. Okay, so here comes the boiling crude oil. So as the oil boils off, goes into the vapor phase, all of the different compounds, everything that boils under 370 degrees Celsius, which is very hot, is going to make its way into this chamber. Okay? And since this chamber is only 370 degrees Celsius, anything that has a boiling point that's 370 degrees or lower, right, would get stuck in this chamber and settle out into this, form a liquid, and that liquid would be pulled off into here. So that's the heaviest of all the compounds. It's called fuel oil. So that goes to two different places, right? One place that fuel oil goes to is industry. They call it bunker oil. It's very, very cheap. And the other place that it goes into is the better grade of it goes into home heating oil. So home heating oil is someplace between these two, fuel oil and diesel fuel. Okay? So now the lighter compounds, the smaller molecules, something like maybe C12, C13, can make it up into this chamber because their boiling point is someplace between, it's got to be higher than 300 degrees but lower than 200 degrees. And those ones will precipitate out and form condensation inside this chamber. That condensation will drip down into here, make a puddle of liquid, and that liquid can be pulled off, and that's the diesel oil. Okay? The compounds that are even lighter than that, so now we're getting to stuff like maybe C10, C8, will make it up into this chamber. They will have boiling points someplace between 200 degrees and 150 degrees. And those ones will settle out into this chamber. They'll form condensation along the walls, and all that condensation will drip down into this section. Notice these pipes are a little bit higher, so when it drips down, it'll collect in here, and then gravity, you can just pull off that, and that fraction is called kerosene. The stuff that makes it one level higher than that is the stuff that we put in our cars. It's the lightest, most clean. Okay, it's completely clear. That stuff is called gasoline. So gasoline has a boiling point about 150 degrees Celsius. So it would boil. Now, we're not burning it, right? This is completely in the absence of oxygen. Whatever condenses inside this chamber, anything between 150 degrees and 20 degrees, which is room temperature, all of that precipitation and condensation will settle into here, form a liquid down at the bottom, and that liquid will drip into this pipe, and that's the gasoline. So you're pulling off gasoline from here, you're pulling off kerosene from here, and you're going to pull them off at the same rate that you make that. So you can keep this thing running 24/7. As long as you keep on putting crude oil into here, you'll separate the crude oil into different fractions. This is the heavier version, then the second heaviest, third heaviest, fourth heaviest, and then all the way up into here, which is natural gas. So you can collect this natural gas. Sometimes, especially in the old days, they used to just burn off the gas up here, which is such a waste, right? So now we probably have better ways to collect it so that we don't have to flame off any of the gas, because that's totally useful natural gas that could go to homes, all right, or go to cooking. All right, so that's kind of the picture of the fractionating column. Let's go back to this and just talk about it where it is in the notes. So here comes the crude oil. These are the heaviest molecules, the longest chain molecules, the ones that boil at the highest temperature. Then you have things like lubricating oils, which are waxes. Vaseline would be in here. Then you have industrial fuel oil. Some people call it bunker oil. Then you have gas oil number 2, which is the domestic fuel oil, and diesel. Then you have raw kerosene, which is finished kerosene. And up at the top, you have the gasoline that goes into gasoline and aviation fuel. Those are the best products. So these guys are the least viscous. They're clear. Pump them right nice and clean. Pump them right into your car. When you burn them in your car, you don't get any byproducts. Your gas tank is not dirty at the end. It's completely clean when you have a totally empty tank, right? Your gas tank is beautiful. Just smells a little bit of the vapors, but a gas is a very clean fuel. In fact, you can almost use it as a solvent. Okay. All right. So figure 8.2 on page 203 is the next thing that I want to go over. So let me go through that one. Oh, I got to get the old book. Sorry about that. So this is just a different version of the fractionating column, right? So same idea. Here's the tower. Here comes the heaviest stuff, just not as much detail as the other one, okay? So what are you supposed to know from this? That these are the muddiest, heaviest, cheapest, least useful of the materials, all the way up to the best, right? Up at the top, which is automobile and aviation fuel, okay? So the automobile and aviation fuel centers around, it's probably carbons that are something from 6 carbons long up to about maybe 9 or 10 carbons long, C10. Okay, this looks like a G, but I'm going to change it to a C. Okay, so that's the fraction, that's gasoline, maybe C5 to C10, 11, let's say something like that. Okay. All right, which centers on octane C8. Okay. All right, so next thing that I want to go over is figure 7.10, which is a view of a petroleum trap. So inside the Earth, whenever you have this kind of formation, which is called an anticline, so this is the surface of the Earth. You can consider this stuff way up here as the topsoil. So what happened is that different layers of sediments have formed in the Earth over time, right? So this material, this material, this material, and this material, kind of the oldest, and then they bent, okay? And so what you need is to create this dome-like structure called an anticline, and these exist all over the place. Anytime you have rolling hills, you're going to have the Earth that's going to fold because of pressure in this direction, right? So not only in some places you're going to have anticlines that look like this, there's going to be other places, so here's the anticlines, okay? Other places you're going to have right next to them, you're going to have synclines, you're going to have downward places where the Earth bent, okay? Well, these aren't very good for collecting collecting crude oil. These are the kinds that are going to collect it much better. All right, so let's go through it. So if I read this to you here, it says a typical petroleum trap. The upper boundary of the trap is an impermeable layer of rock called a roof cap rock. So it's going to hold in, right? This roof cap rock is not going to let the gas escape that's stuck inside there. So what's going to happen is between these layers and these layers, which are both impermeable, you're going to get like a bubble. And inside that bubble, it's going to fill up with water, and the water is going to push the oil up to the top of it because oil floats on water. So all of this rock has the organic petroleum material, right, the crude oil in it. And over time, the crude oil has leached out and went into the water layer, but oil does not mix with water, so the oil layer rests on top of the oil. And then on top of the oil, any natural gas that would have formed, called an associated gas with the oil, is going to move to the top of that because gases are lighter than oil or lighter than water, and they're really going to float to the top. Okay? So if you put an oil well right here, if you could find these kinds of structures, you could puncture through these two and collect the oil from down here, and then eventually the associated gas that's on top of it. But mostly they're going to put almost, you consider that pipe looks like a straw and go all the way down into the oil layer. And on the next page, I'm going to show you what some of these pumping devices look like. So originally, you make an oil derrick, which looks like a giant drill that goes down into the earth, and then you line it with a pipe. And then after it's lined with a pipe, you pump this liquid oil out. Okay, so that's figure 7.10. That's the petroleum trap. Okay, figure 7.11 are the different ways that you pull the oil out of the ground. Okay, so again, you have these graphs in your chapter 5 notes, okay, on Moodle. Okay, so here's after you build the oil derrick, which is the looks more like this, right? Here's the surface of the ground, and you think of this big structure that's made out of steel. It's maybe 100 feet high, right? And you're drilling, right, into the ground. After you make it to the oil, here's the gas, here's the oil. Then you take the oil derrick away and you bring it to another site to drill another gas port, right? Or drilled another well is the best way to say it. And you're going to replace it with something that's just going to pump the gas out of the earth. So you take this away, you don't need this anymore. You don't throw it away, you just put it on a truck and go to another site. You leave the pipe in the ground, and now you put a much simpler, smaller device into the earth that's designed to suck the oil out of the earth and pump it into some kind of a chamber. Then a truck can come over and pull it away later on. So those are going to look like this. I'm sorry for my bad picture. Okay. So the first one, these are oil recovery methods. So how to pump more oil from the ground. So primary recovery pumps out the first 15% of the original oil in place. So here's the material, right? And once I get to the oil, I can only just do traditional pumping, right? Of just simply sucking the oil out of the ground without somehow enhancing it. I can only get the first 15% of the oil. So that leaves 85% of the oil still left. So as this thing goes up and down, and it kind of goes like this, right? It's pulling or pumping each cycle. Every time it pulls up, it's going to pump some oil out of the ground, and that oil is going to go into some kind of recovery tank. It's going to get pumped into here, and we store the oil until a truck can come by, okay, and pick it up, right? Unless there's so much oil in this oil field that they actually pipe it into a place, but I don't think they do that much. I think they then bring it over to a distribution center. All right, so after that first 15% is gone from the primary recovery, what are you going to do next? You don't want to leave 85% of the oil still in the ground. That would be pretty wasteful, right? You made this big hole in the ground. How are we going to get the rest out? Okay, so the second thing you do is called enhanced oil recovery. Okay, so the enhanced oil recovery, over here, the secondary recovery is water flooding may pump out another 20% of the original oil that was in place. So now what you do is you push in water over here. You have two pipes, and the water goes down underneath. Remember, oil doesn't dissolve in water, and the water pushes the oil back up here so that you can get the next whole bunch. So how much can you get out of that? You can get another 20%. So 20 plus 15 gives you 35. So now you have 35% of all of the oil. What's left after you do this idea of pushing water down underneath the oil so the oil rises to the surface and you can collect it? Now you have 65% of it left. Okay, so the first two methods, first one gets you 15%, the second one gets you another 20, so 15 plus 20 gives you 35. So still have 65% of the oil still in the ground. So the third method that they're going to do before they give up is, instead of just pumping water into the ground, they're going to pump steam into the ground. So this hot steam is going to loosen up the oil that's in the rock. The oil is going to move through water and sit in a layer on top of the water, and you're going to be able to get another whole bunch of it. How much more can you get out of this? You can get another 10%. So the original 15% that comes out easily, comes out naturally, the 20% that you have to pump out with water, plus the 10% that you have to pump out using steam. How much does that add up altogether? That's going to give us 45%, right? So 45% of the oil can be pulled out of the ground with these three methods. That still leaves 55% of the oil left behind. So a lot of times after they abandon a particular well because they have as much as they can get out economically, they're still leaving a whole bunch of oil behind. So we may be able in the future to go back to those original wells that are in Texas and Wyoming that we've given up on and use more enhanced techniques and get oil out of old oil wells with better techniques. Okay, so we really leave half of the oil in the ground whenever we do one of these pumps, which is kind of wasteful, right? Because you just think about the environmental damage. This is on somebody's farm, right? It's ugly, trucks rolling in and out. So it would be great if we could pull 100% of the oil out of the ground. If we're going to drill and make these oil wells, might as well get as much oil as we possibly can out of them, not leave half the oil in the ground. But right now, most of the commercial wells are doing exactly that. They can't economically get 100% of the oil out, so they're getting way less than that. Okay? So those are three terrific pictures of the process to suck the oil out of the ground after you originally find it. Okay? So those are the oil recovery methods, which are figures 7, 11. Okay. All right, so next thing that we're going to talk about is, well, you know what, this is kind of neat. I'll go back to these. Okay, so next thing that we're going to talk about is transportation logistics. Okay, so when you find the oil, how do you get it to the places where people need it? Well, one of the things is, especially in the United States, once we have come up with these enhanced mechanisms and done a lot of fracking, a lot of the fracking has associated gas with the oil. In fact, fracking is mostly to get natural gas. So once we collect it, we need to sell it to other countries, because the United States, and this is a good thing, is becoming a net exporter of natural gas, right? So we've found a lot of natural gas in the last 25 years. And how are we going to get it to other countries that need the natural gas, places that don't have their own natural supply? Well, if they're across an ocean, we don't have any pipelines that go underneath the ocean. So if you have liquefied, if you have natural gas and you want to get it to China, South Korea, or Russia has their own supply, but you want to get it to countries that islands that can use the natural gas, the smartest thing that you can do is you can liquefy it. Okay, and the reason is, whenever you turn something from a gas to a liquid, it goes into a condensed state of matter. So it occupies much, much less space. In fact, it only occupies 1/600th of the volume of the gas that flows through our pipes to our house. So that's amazing. Okay, so what do you have to do to it? You have to bring it to a processing plant. So a lot of times we have these processing plants in Alaska, Washington, California, mostly in the West. Actually, you can probably have some in Virginia, and Pennsylvania and Delaware, where you can pump the natural gas in the gas state out of the fields that it's created in. Okay, and then once that natural gas gets to the coast, you have a liquefied natural gas plant that basically cools down and pressurizes the gas, to minus 162 degrees Celsius, which is minus 260 Fahrenheit. So incredibly cold. Okay, at that temperature, the gas liquefies. You put the liquid gas into a giant tanker transport ship, right? And since the gas is so condensed and it's in the liquid state, basically one ship that has liquefied natural gas on it can take as many gallons of this liquid natural gas across the ocean as 600 ships that would have just had pressurized natural gas under it. So it's a huge advantage. We don't want 600 ships crossing the ocean when we can only have one ship cross the ocean. So picture in Seattle, a station where ships could dock. I'll show you what they look like. Right, these things are huge. Right? They look like oil tankers, only instead of being designed to carry oil, they're designed to carry liquefied natural gas. So inside these giant tanks, right, looks like there's 4 or 5 of them on this ship. This thing is just going to be filled up with liquefied natural gas. So it's going to fill up in the United States, and it's going to go across to a country that doesn't have enough natural gas. So I think China and Korea are 2 of our biggest customers for this. Once it gets across, it gets warmed up, which is very easy. You just warm it up naturally. It goes back to the gas phase, and now it flows through pipes into people's homes or to factories that need it for different processes. Okay, so you are responsible for this concept. Okay, it's called LNG, liquefied natural gas. And since 2010, there were 33 liquefaction plants worldwide, and their function is to do what? Is to convert natural gas into liquefied natural gas so that it can be shipped around the world. Okay. Couple of other technologies that we want to talk about before we move on. So these would be considered sort of modern places where you would find fossil fuels. So the first place are called shale gas. So this comes from fracking. Okay, so if you read in the old book, and I'll show you the particular diagrams that go with it, on page 212 of your book. Actually, take that back. This guy. Not in here. It's this section right here. So if we read through this, it says the United States has but one terminal and is considering liquefaction plants for what might be an export market based upon the presence of additional reserves. Britain has long-term contracts with such suppliers as Qatar to provide 25% of its electricity from liquefied natural gas deliveries. Additional unexplored land-based resources of natural gas in the United States can be found at substantially higher prices. Such sources are from trapped gases within coal beds and the Devonian shale that underlies much of the land in the eastern United States. So I'm going to see if I have a diagram that shows you where that is. And you see it's pretty close to home. Okay, so across here, right, this is where a lot of this is actually a coal diagram. So I want to see if I have places where the fracking is. I'm going to have to take a break from that and see if I can show you that later on. Okay, so what I'll do instead is, let me just go through, all right, so in upstate New York, it's called the lower tier. I can kind of draw it for you quickly. All right, so everybody kind of knows New York, sort of. Not bad, right? That looks like New York, right? Here's Manhattan. Here's Long Island, right? Here's the Bronx, right next to Manhattan. Okay. Here's New Jersey. And this is Pennsylvania, right? So this is Pennsylvania. And here we are. And here's Bergen Community College. Right? Let's just forget that this line is here. All right, so in this region here, partly in Pennsylvania and partly in New York, there are a lot of shale gas resources. So basically, very controversial, because in order to get this natural gas out of the ground, it's actually mixed into the shale rock. So the shale rock is kind of permeable. So if you're looking at a cross-section of it, you could almost think of the gas as being kind of like the rock is like a sponge, and the gas is kind of in the rock itself, right? So this is almost like a solid piece of rock. And then here's the topsoil. So what you have to do in order to frack is you need to pump in, right, to drill 2 wells and push a fracking liquid, which is mostly water and some chemicals, right, called lubricating liquids, right? You pump them into the ground, and they kind of push and break, and actually there's also some sand in there too, right, to kind of embed and make these spaces bigger so that the gas gets pushed in a particular direction, and you put, this is the in well, and then you pump out the gas over here, okay? Now the problem is, the reason why this is so controversial is, you put millions of gallons of this water, chemicals, and sand into the earth to capture this gas, to get this gas to come out this pipe over here. And a lot of questions about what happens to all of that liquid that went into the ground. A lot of it is supposed to be recovered by the companies. They pull that back out of the ground once they're done. But some people have made claims that on their farms, remember, the water table is up here, right? The gas is much lower. This is thousands of feet, maybe let's make it 2,000 feet under the ground, right? But a few hundred feet under the ground is the tables where people get their water. So, if any of that fracking liquid and water and sand leaches into the water table up here, then someone's well on their farm, and most people out in these rural places get their water from a well, they're going to get all of this polluted materials in their drinking water. So that's one of the reasons why it's so controversial. Okay, but it is this shale does exist. It contains a huge amount of natural gas that can at some point be extracted if we need to get it. It's expensive. It's controversial because of the environmental damage it may do. But again, it's how you do this process. If you could figure out a way to do it in a totally sealed up manner, that whatever you're working with doesn't leak out into the environment, if they're incredibly careful with how they do it, right? And they do it responsibly. So the oil companies, imagine that, actually working responsibly. It is possible to do this well. If you do it poorly and you pump the fluids into the ground and you don't watch where they go and you're not testing and you're not careful, then you can make environmental disasters. So It's not just a question of is fracking good or is fracking bad, it's how you do it. Okay? If you do it responsibly, you probably can engineer your way into a useful source of natural gas. If you do it irresponsibly and cheaply, then you're going to do more damage than good. You're going to ruin this person's farm, which sits on top of the land that they leased it out. The individuals who live in this area wind up getting cancer. Remember, there's a whole farm and stuff up here. Look at where it is again. You're in, all right? This is the southern part of upstate New York, and this northern Pennsylvania. There's a whole lot of agriculture up here. And so the fracking would be done under the ground and the farming would be done right on top of it, okay? A lot of these places are already used for agriculture. Okay, I'll load a fracking video for you and it'll explain a lot better than I did. Okay, so that's the shale gas. Another resource are called gas hydrates. So these are kind of interesting. So gas hydrates are methane gas that's trapped within the crystal structure of frozen water. So this kind of resource would be in the Arctic and the Antarctic. So just think, over time, right, as the ice accumulates in the Arctic, right, and I get hundreds of feet of ice, you go through seasons. So the ice in the wintertime builds up. In the summertime, there's life on top of it and some vegetation and stuff like that. And plant material is going to slowly get trapped inside that ice for thousands, maybe even millions of years. So if you core down into the ice, you drill down into the ice, and you pull some of the ice from way down here, bring it to the surface, and let it melt in a closed chamber, right? Then all of that trapped natural gas, right, from the decaying plant material and animal material over time, when the water from the ice melts, it's going to get trapped in here and you're going to wind up with natural gas. So, in incredibly old samples of ice that are in the Arctic, there is natural gas that can be extracted. Now, again, this is an expensive process. There's not going to be a huge amount of it every time you do this core. So this would be considered a resource that wouldn't be worthwhile to use yet, but maybe in the future it's something that we can do. So the gas molecules like being dissolved in the frozen ice. There's a strong affinity of the methane molecules. I'll show you this up here. These are the methane molecules, and there's going to be water molecules all around them. And that's going to be kind of frozen in. So there'll be one methane molecule, a whole bunch of waters. There's another water, here's another water. And then over here, there'd be another methane molecule, CH4, and more. So the natural gas is frozen into the water. When the water melts, it becomes a liquid and the gas escapes. We don't want the gas to escape into the environment. We want that gas to be trapped somehow. So we want to make some kind of a chamber where we do the melting so that we can collect this gas. If the gas escapes into the environment, natural gas in the atmosphere is a greenhouse gas, like carbon dioxide, so we don't want it to just escape directly into the environment. That's one of the problems with the polar ice caps melting, is as this melts, it releases just naturally the methane gas into the environment. Okay, so this particular technique, these gas hydrates are a future resource that we could possibly use. Okay, so that covers everything in terms of what you're responsible for understanding the petroleum industry. The next topic is on coal. So let's talk about the process that makes coal. Natural gas and in particular petroleum comes from fossil fuels that originated from plant material, mostly algae that collected in the earth and was buried for millions of years, and then we find that resource. Coal is not originally, for the most part, from algae. It's going to be from plant material. Okay, so whenever plant material gets buried in the ground and undergoes a metamorphose that changes it, right? It's like a metamorphic rock that under heat and pressure for thousands of years, that plant material goes through this process. Okay, so plant material that accumulated in swamps millions of years ago. So think of ferns and stuff like that. That plant material gets trapped, covered with water, so that it can't decay naturally because no oxygen can get to it. And it makes a substance called peat. So there are peat bogs in the world now. We always think of peat bogs in Ireland and Scotland and any other low-lying country. So it's organic material, kind of muddy and kind of right on the surface. If you dry out that peat, you can burn it and heat your house. So it's a long-standing tradition in those countries that some people actually still use peat to heat their homes. Okay, but if the peat doesn't get pulled out and it gets buried further under the ground, more heat and pressure and millions of years, the first form of coal that it goes to is called lignite. So lignite is the youngest kind of coal. It has the least carbon content. It's the softest, and some people call it soft coal. And you can dig it out of the ground. It has a value. It's considered coal. You can burn it. So that's one material, one type of coal. So the three kinds of coal, the first one is lignite. Okay. All right, next kind. If you don't collect it at that point and it stays under the earth, more heat, pressure, more millions of years, it becomes subbituminous coal. What's happening to it? It's getting harder, more compact, less water content, more carbon content. After subbituminous, it goes to bituminous coal, so more millions of years. Again, it's going to get harder. And after bituminous, the last type of coal you're responsible for is anthracite. So it goes from lignite to subbituminous to bituminous to anthracite. Okay, I'm going to show you this figure on page 216. It's at the bottom. See if I could just autofocus it a little bit. So it ranks the coals, right? The last one, they're all considered a type of rock, right? Anthracite would be considered a metamorphic rock, where bituminous and subbituminous and lignite would be considered a sedimentary rock, okay? So the other thing that you could have over here in the ranking is how many millions of years they were under the ground and under what conditions. So the most heat and pressure is going to be needed to form anthracite. Bituminous is going to be less, subbituminous, and lignite is going to be the youngest, softest, most like organic material. Okay, so what's the percentage? Remember, these are hydrocarbons. Okay, so what percentage of the lignite is carbon content versus hydrogen versus whatever oxygen is in the coal? So this is going to be 30% carbon. Subbituminous is going to be 40%. Bituminous is going to be someplace between 50 and 90%. And anthracite, a little bit hard for you guys to see that, anthracite is 90% carbon. So most of the hydrogen has been removed from the compound. Well, in terms of how much energy it can give you per pound, so when you burn it, you burn 1 pound of lignite, you get between 5,000 and 7,000 BTUs of energy. Anthracite, look at that. This is 7,000, this is 14,000. So anthracite, for a pound of it, you get twice as much energy. So if you're using this to heat your coal, you'd need to bring in half as much in the winter to do the job. The problem is, the higher the percentage of carbon, the more greenhouse gas it's going to give off. If you look at the oxidation of any organic molecule, the carbons all go to carbon dioxide. The hydrogens that are in the hydrocarbon all go to water. Well, water isn't a greenhouse gas. Carbon dioxide is. So anthracite, right, which is considered the most valuable form of coal, also is the worst form of coal in terms of delivering greenhouse gases. So all of the coals are bad relative to petroleum or natural gas. Natural gas is going to be the best type of fossil fuel. None of them are good. They all create greenhouse gases. But natural gas is certainly going to be better than petroleum. And petroleum, as much as we don't like it, is going to be better than coal. Coal is the worst. And of the coals, anthracite is the worst of the coals. Okay, so that's types of coals. Okay, last thing, this is kind of neat, is you can make oil from coal. So that's called synthetic oil. And this has happened a few times in history where people have been cut off from any petroleum reservoirs. And so what they did instead was make synthetic oil from coal. So one of the places this happened during World War II is in Nazi Germany. When the Germans lost their access to petroleum resources in the world, they converted many of their factories into these oil synthesis operations. Right? So they basically conducted chemical reactions on the gases that came off of a coal and liquefied them. So we won't go through the chemical process, but you can make a liquid fuel from coal. Okay? Takes a lot of work, takes a lot of energy, not really, environmentally friendly, but you can actually make a product that looks like gasoline that originally came from coal. So it comes from coal gases. The other thing that you can do is coal gasification. So in coal gasification, what you do is you expose the coal to heat and steam, and in the absence of oxygen, and you create a gas that has hydrogen in it, natural gas, and carbon monoxide. And that coal gas can be used to heat homes. In fact, in Europe, and especially in England, up until the 1950s, most of the homes were heated with coal gas. Very dangerous stuff because of the carbon monoxide content in it. And the last thing that you can do, so you can gasify coal, you can make synthetic oil from and gas from coal, and then you can also liquefy coal. So you take coal, heat, and hydrogen, and you can make, a liquid product out of coal that resembles a gasoline, okay, or resembles diesel oil. So these two things are kind of very similar. You can make the synthetic oil or coal liquefaction. Here's some future sources of oil. So we talked about the shale gas on the eastern part of the United States. There's also shale oil. So shale oil, these are going to be mostly in the western part of the United States. And I can show you where that is. I think that one diagram had that. It's going to be, Wyoming is a big resource for this shale oil. So again, this is going to be kind of a messy, not a simple process to get the oil out of the ground. So it's only going to be important when oil prices are high. So if you look at these western states over here, right, this is Nebraska, South Dakota, North Dakota. This is Wyoming. So you can see all of these deposits in Utah, Colorado, and Wyoming. Especially this western part right here. It's called the Green River Valley. And one of the products that's there is shale oil. So it's oil that's trapped inside decaying vegetation in sedimentary rock. It makes an organic compound called kerrigan, and that kerrigan can be extracted and converted into oil. Kind of like the tar sands that are in Alberta, in Western Canada. You would only do this after you ran out of all the traditional sources of oil. It's very expensive to do this. Again, so it only really, these kinds of places, these oil fields are only used when gasoline prices are very high. Okay, but it's there, and you can use it if absolutely necessary. All right, so last type of petroleum extract, again, very expensive to get out. It's sitting right in front of us. It's in Alberta, Canada, and they're called the tar sands. Or some people now, it's a little bit fancier name, they call them the oil sands. So basically, you have what looks like sand, and it's just oily sand. So there's oil kind of coating this sand in a whole region of Canada, miles and miles and miles of it. It's right on the surface. The work is not finding it. The work is moving it to a plant, or bringing it to a plant, and heating it up in the presence of a huge amount of steam. And basically, you're just going to extract the oil that's on the surface of these sand particles, and the oil is going to move to the liquid phase, and you're basically cleaning this sand. So at the end of it, you go through a huge amount of water. That water winds up to have some oil in it, and it's really polluted. Hopefully you guys can, I'm still going. Okay, my screen went off. And so that's the biggest problem. This is a huge environmental issue. One, it's very expensive. You have to use a lot of energy to heat up that water, boil it, to clean this tar sand, to get the oil off of it. So that's the first problem. How much energy does it take to get the energy out? So this is going to be a very energy inefficient process. The second issue is all of the water that you boiled to make the steam, when you recollect that, it winds up in polluted water that you can't put back into the ground. So basically, they've created these man-made tanks, or they call them lagoons, and they're just filling up these lagoons. Now, the lagoons don't drain into any rivers or estuaries. They're not supposed to. There's a lining at the bottom of the lagoon, either a natural clay bottom or maybe even a plastic tarp or something, so that the water just sits there, this polluted water. So you're basically taking the tar sands over here, using up a huge amount of clean water to make this polluted water. So again, the jury's out. Is this worthwhile economically? And more importantly, what damage does it do to the earth? How much clean water that someone could use on their farm or drink are we using to extract the oil from the tar sands? Again, a huge issue. Okay, so that's it. I'm going to stop this video now. That's 53 minutes. That's enough. And I'll come back to a couple of practical things that we're going to do in a little bit. One of them is calculating the delta H, which is the enthalpy of a combustion reaction from the bond energy. So I'll teach you how to do that. And then the second thing that we did that we need to practice probably a little bit more is drawing the energy diagrams for the combustion reaction and showing what the heat of the reaction is and what the energy of activation is. Okay, we'll see you on the next video.